So in this session, we'll be looking how initially data enters into transformer and over the time, how it get changes, like how the size of the data gets changed once it start moving from multi-head attentions to layer norm and then to feed forward layer, and how these self-attention chunks are used later on in encoder and decoder itself. You all can visit our repository first of all, which is, I think, shared with you. I'll just show it here. And you can just clone it. I think every one of you have link for this. These are just initial files. After this, you can start coding with me, whatever I'm doing. Is everyone done with cloning? I hope everyone is done. So can I start? I'll just revisit few part from yesterday's session, which Professor Manish shared. I'll just visited the same reference which he was using. So if you all remember, initially we just have a initial vector x for whatever token or whatever batch we are working with. And later, after on, once it cross the input embedding and positional encoding, it converts into three different vectors: query, key, and value. This process happens after we just multiply it with the respective linears layer they have, whatever it's whether WQ, WK, or WV. And what we get inside our multi-head attention is these three vectors: query, key, and value. So the initial file which we have here is self-attention itself. You all can open it in your VS Code or whatever editor you are using. So inside this multi-head attention, if we just zoom bit, we'll see that there are parallel this scale dot product itself, self attention layer itself, which are stacked over each other. It depends on whatever the number of heads we have. We have whether 8 head or 12 head. That will be the parallel number of these self attention mechanisms. Again, itself, we can see that we have value key and query pair itself. When we come inside the scale dot product itself, we have this kind of structure here. Let's go a bit theoretical itself, and after on we'll start coding. Initially, we'll getting query and key. We'll take a matrix multiplication of these two vectors. We'll scale them down. I'll tell why we scale them down. We use mask, which is optional, because if you anyone of you remember why it is optional, anyone can answer from yesterday's session. Yeah, for encoder, we don't need any kind of mask, but for decoder, we do. Since the mechanism is same itself, we keep it as a optional flag, which we can turn on or off as per our requirement. Later on, we have softmax to get all the probabilities of each token, whatever, to find out which token is getting most of the attention itself. And then we have final matrix multiplication from the attention we got and the earlier value pair we have. So we have two components in our transformer. One is encoder and one is decoder. While decoding the stuff, we don't want this mechanism itself to look into a future. Let's say you are doing some translation task and you are training your model, or you are just normally inferencing itself. And you are translating, let's say I'm going to the car. If I translate into Hindi, I'll just put an initial word itself. Traditionally, it is just a start of a token itself, but let's say I put "मैं." What I want is transformer doesn't look into future and predict next word itself, "मैं car में," and then it will again go into decoder itself. But while encoding, we don't require any such scenario.
It's present inside the scale dot product attention.
Yeah.
Common, right? But what we are talking as the self attention that is present in the decoder is a different mask multi-attention where, say for example, if my name is Ankit is been converted to say French, it's Jamapal Ankit. So for example, my name is Ankit is been converted to Jamapal. I think the output of the Jamapal, that's the output that the decoder has already given. So that is the input that has been passed to the decoder again. So that the decoder also understands that Jamapal had already been created by this particular transformer.
Yeah.
And we mask what is the next word.
Yeah.
That is the mask that particular decoder is having.
Yeah.
But when it comes to self-attention, the mask, I don't.
There are two types of self-attention in decoder itself. One is just a mask self-attention. One is the cross self-attention. This masking happens in mask self-attention. In cross self-attention, you get inputs from encoder and decoder itself. You just mix up both the concept together.
Is there a possibility that, say for example, there are 4 tokens, and therefore my token is going to have an attention matrix being formed based on the Q and key value, where which will combine together, we get an attention matrix, right? And this mask, can it be just a speculation here? Can this particular token, in some case, be masked in cases of attention, calculation of this attention mechanism?
While in decoder part.
Exactly. So like my name is Ankit, and say for example, is this mask, because that has very less meaning compared to the matrix. Can that be?
I'm not getting your point, to be honest. This is just a normal triangular mask. You can't jumble it up कि आगे covered पहले mask कर दिया, पीछे का बाद में करा. It just, once you start producing a words, it will keep on unmasking the next word. That's it. I'll explain in decoder part itself. I'm just telling there are this mask flag itself, which happens in normal scale dot product. How this works into formula is, if we go back to this thing, we have normal x, which is converted into Q, K, V. We do just a normal scale product, just we scale it down with the root of whatever the dimension of our query is, the whatever it can be. Now in this case it's key, but dimension of all three are same initially in transformer. We just do a softmax, and then we finally multiply the value of softmax in the initial value itself, and we get a Z1. Similarly, we can get Z2 and Z3, whatever. Coming to formula itself, it will look something like this. So we just have to implement formula itself, because we can't just wait for one token to come, another token to come. We are taking complete batch itself for query key and value. Coming to our code, these are just dummy values we have, just to showcase how the dimension of any vector changes over the time. Let's start by defining what will be the length of my sequence. Length, by length I mean, in this example, if let's imagine this is a sequence of length 2 with dimension 4. There are two words here with the dimension 1, 2, 3, 4. Coming to our code, it will be length 4, dimension 8. So I have a sequence of 4 words, which embedding or the D model itself is 8. I think in case of other models, let's compare with GPT, which has a dimension of, I think, 768. So it's that kind of dimension. So instead of 768, I just have a dimension of 8. And in my batch, a maximum sequence, I can have a size of 4. So it will be sequence length 4. I'll create three different vectors from here, query key and value, which will be something like this. I haven't multiplied initially with WQ, WK, and WV, because if we look close to this image, I'm getting this thing here. So there's no meaning of starting from here, multiplying and creating new, because this is just for a demo purpose. So I have directly created query key and value of dimension 4 cross 8. You all can run itself on your editor also, just to be in track with me. So our query key and value will look something like this. Now for each sequence, I have a query key and value. And for each sequence where I have 4 words, I have 1, 2, 3, 4. Similarly, for in each form for query key and value. I have to implement this formula now for attention. I'll start with initial matrix multiplication, which will be just simpler Q into K transpose, which is also showcased here, query into K transpose. I'll get the upper numerator. Now the question is, we need to do this thing, scale down it also. The reason behind scaling down it, let's say I have to find variance of query and key, the initial two vectors which I have, the 2-dimension vector which I have. If I look, I have a variance of 0.6 or 0.6, like 68. These are two different variants. But once I do a matrix multiplication, my variance will shoot up. It will be 3.05. And if I keep on calculating over this, like softmax and then further attention, it will be very far away from the original inputs itself. So I have to scale it down using the formula, again, under root of the dimension of key itself, which in our case will create a variance, which is again in close of each matrix variance itself, matrix in the sense query and key itself. Now, this is the whole and core purpose of scaling it down. The complete denominator part is to bring the variance as down as possible.
Two questions. Why this?
No, like I don't have a core concept why they use this self in formula, because like, I mean, after matrix multiplication, might the summation of these metrics which we have received itself is more than what original format was. Like if we multiply 2 into 2, it will be 4 itself. So that can be the reason why they are far away from the original format itself. But this is just a formula implementation what we receive from paper. So this is the whole reason why they just use this denominator just to scale down the variance. That's the only reason. Now I have a scaled version of the complete numerator and denominator itself. Coming back to formula, I'll just introduce the softmax on this. Before this, I'll just show what that optional mask was there here. This mask, which was optional, how it can be presented. This is not the original mask. This is just to show that for each sequence, initially I'll be just looking at first word, then I'll be looking at first two words, whether like I'll be receiving new word from the generation of decoder itself. Then I have initial three words and then complete sequence itself. I can't just add this scale, add this mask to my attention, which I have received just now. Because if I just add it, there will be no change where zero values are there. So I have to create a lower triangular matrix itself in my scaled value. So instead of 1 and 0, I can use, if anyone can make guess. Yeah, because I want to bring it as 0, close to 0 as possible. So I'll just use minus infinity instead of 0, and instead of 1, I'll use 0. So this will be my new masking, which will be in form of 0 and minus infinity. When adding the mask to the scaled value which I have received, our matrix will look something like this. Right now, this matrix doesn't make sense, but once I apply softmax over this matrix, again, I hope everyone knows the formula of softmax. That's the only formula itself, which is something like this. Once I apply softmax over this, I'll get softmax of scaled plus mask matrix, which will be a lower triangular matrix. How this thing, if I just make a guess here, these are not the actual embedding of any token, but just to explain these metrics, I'll just say that initially when I have just one word, my transformer is completely focusing on first word because probability is 1. When I have two words, my transformer is focusing on more on the first word and then on the second word. And it keeps on going, like if I have this last complete sequence itself, my transformer is focusing more on the last word than on this word. How this looks visually is like, if you guys remember from yesterday's session, this can look something like this. This word has most of the probability in this sentence because it's a deeper green shade. Then these words have less attention because of lesser shade. So this is, again, we can imagine this will be having a probability of 0.00 something, where in case of tire, it will be 0.5 or 0.2 something, which will be the highest probability we have. With the end of this, we receive our attention, which is the core thing we were looking for in transformer. And once I get attention after this softmax, I'll just matrix multiply the original V value I had. This is just a normal matrix multiplication I'll be having. In the end, I'll be getting my new V value, which will be the final output I'll be receiving from transformer's self-attention layer itself. Again, this is just a complete functional implementation of this. And if I just pass my values of query key and value, I'll be getting these dimensions. I hope everyone, yeah. What is the what they are trying to say? I can just whatever I have learned is like they are firstly holding the original format, original representation of those vectors, whatever the x was, which was split into query key and value, and then to continue with those vectors, they are just enforcing the attention which we have got and the original vector which we had, just to hold the meaning of the original embedding itself. So that's why instead of just using attention directly, they are multiplying with the original format we have. Again, this is the same concept which we use in residual connections. I mean, in residual connection also, we just skip that layer itself and we directly add it with the new V. So they are just using the small residual connection itself inside these scale product. How this masking is done? How this masking is done, or what is this masking? So basically what we want is, once I have my like this scaled value, which is again just a multiplication of all the query and key divided by that dimension. Uh, what I want is like if I'm feeding this matrix query in this scaled value itself, I want that initially only first token is visible so that the like decoder part can predict the next token. If I just initially showcase all the token itself, it will calculate the query key and value like further on instead of just predicting the next token. So we just hide the future token so that it can keep on predicting the future tokens. So like here, if I start when model initially predict the first token, the all the attention will be on the first token itself. When it keep on predicting the next token, it will start finding like which is the most valuable token here, and then it will provide the probability on basis of that. And over the time, it will move like this. This is the self attention, which will be again over the time used here in multiple layers. In this code, I have skipped some part. I'll be happy if you can start coding and fill those parts. I'll tell which is missing. So coming to, I think, now instead of just creating one chunk of query key and value using this query key and value, what I'll do is I'll have multiple heads here. I'll be having multiple these linear layers, WQ for ith head, and I'll be creating different pairs of query key and value. For each head, I'll be getting my one Z. Z here is new V, which I derived from multiplication of the attention and the previous V itself. Here they are calling it Z. For multi-head, I'll be getting multiple Z values, 0 to whatever the nth number is there, n minus 1. I'll just concatenate all the Z values, new V I received. I'll be having one matrix, WO. The idea behind this matrix is I'll pass my Z to with this WO. This is just a linear layer. The idea is that when this Z0 was getting created, Z1 was getting created, Z2 similarly, they were unable to communicate with each other because they were in different head, parallel heads. To make these vectors communicate with each other to share their weights, we pass it through this representation, which is WO. And finally, I'll getting the final Z itself from that self-attention or multi-head attention layer. This will be my final representation and will be working for this Z now. This part we have completed. We have to implement the complete part inside this. Instead of creating n different V, K, and Q, I have just for this demo purpose, I have created a single chunk itself so that I don't have to calculate n into 3 linear layer of WK, WQ, and WV. Let's start with the sequence length. I'll just have a single sequence here. My batch size will be 1 because single sequence is there. This time I have input dimension of 512 instead of 8, which I was having in previous code. I'll just randomly initialize my vector here. The size of my vector will be batch size into sequence length into input dimension. What I'll do is, because I have to create 3 different vectors from here onwards for query key and value, and then split it into different heads. I'll just showcase it how it will be looking. My X will be given to all the heads here. Inside the head, I'll be having WK. This is in the scenario of multiple multi-head. I'll just draw the single head itself and then we'll start working on this. Any guesses? What will be dimension of these matrices? What? This is single head. This is for single head, not for multi-head. I'm asking for single head. Let's say my X is of dimension 512. Now, this will be 512. What will be this side? Let's say this is 512. What will be this side? This will be 512 itself. Because I have to create 3 different vector itself. I don't have to chunk those vector down. So once I multiply 1, let's say 1 here into 1 cross 512 with 512 cross 512, I'll be getting 1 cross 512 itself. And I have 3 these layers because I want 3 representations. It will be again same dimension of X. Coming to this thing, again, let's imagine I have 1 cross 512. What will be dimension of this thing? Now let's say I have 8 heads. Five and two cross cross. My final vector will be of size 1 cross 64. Can anyone tell why this is 64 here and one is 512 there? Yeah, so basically we are chopping those complete vector down so that each head get their own fed. So once I have done with all the process, my final V will be also of shape new V, or in this case they are calling Z0 or whatever they have, will be of size 1 cross 64. And when I have to add all the Z0, Z1, 64, Zn minus 1, I'll be having final vector of size 1 cross 512. We are back to the original vector itself now. Just because we are having multi-head, it doesn't mean we'll be continuing with the complete 512 vector itself. We have to chop it down so that work can be done parallelly and in faster way. What I have done in this code is I have just taken a 5 because I'm not creating these things. I told you earlier also in last code also I haven't created this. What I have done is took a bit of shortcut here, is directly created a matrix of, I think, 1536. 1536. This will be query, key, and value. For each head, this will be further chunked down to 512 divided by 8, 512 divided by 8, 512 divided by 8. So now I will be having 8 query key and values respectively of size 64, 64, and so on. I'll be getting this thing here. I'll start showing the code. If anyone has any issue with this thing or unable to understand, can just stop me. What I have done is I started with initial size 512. I just tripled it out to 1536. I have my complete chunk query key and value this thing now of 1, 4, and 1536 dimension. This thing here, because my vector is of batch size 1, tokens that is sequence length 4, and dimension 1536 now, which something looks like this just for a representation. Because I am having like, how many head I have? Just a second. For each head, what I have done is I have clubbed the query key and vector together. So for each head, if I have 64 size query, 64 size key, and 64 size vector, I have just took is at a single pace, and it is 192 now. So I just divided 1536 by 8, which is so I have just chunked the complete 1536 vector into 8 particular head and later divided into each particular query key and value. which comes like this: 1536, split it into 8 heads. I have 8 heads now. 8 into 192 is again 1536 itself. And then later for each query key and value, I just scaled it down to 64. I think this is not here in this code. I'll start running the cells. This is the final size of each query key and value for each head, which will be 1. I have just shifted, if anyone has this thing, like here it was 4 and then 8. 8 was the number of head, 4 was the length of a sequence. I just shuffled it out to get a 8 and then 4, because I have to work on last 2 dimensions itself, which is sequence length and size of each embedding. I don't want head in between because I'm working inside the head now. My final dimension of each query key and value will be 1 cross. For each batch, for each head, I'll be having sequence of size 4, and each token will be having dimension 64. I think this part is being removed from that code that you guys have received. Yeah, this thing is not here. For further implementation, I think you guys have to implement this thing. I'll just take a 30-second pause if you want to go with this thing. With cell? Again, the same scaled dot product again happens in each self itself, because I have received my query key and value, and the same formula will be implemented on each query key value pair for each head. I'll not go with this because in last code I have done this. What does this all means? Yeah, this cell, this thing. What are you asking me? Yeah, this is the cell which is missing. I think this is the only cell which is missing, because I have just divided all the continuous chunk of 192 into 3 different vectors now. Now I'll be treating these 3 vectors as an individual vector of each head. I'll be running through self attention itself. I'll be having mask because I just took it from last code itself. I'll be having attention getting calculated. Now this is the final query key value. The value which I received, that Z0, I think. This thing. This is of dimension 18464. This is the complete, again, scale dot product function. I have a question. If I z0 of dimension 1, 8, 4, 64, what will be the final value of the z which I'll receive? What will be the dimension of final z? If my single z looks like this, zi looks like this with this dimension, what will be the summation of all the z? I'll just show, like, I'll not show the answer, but I'll just show him what I'm talking about. This thing, I'm asking about what this z will looks like, this complete z, sorry. What will be the dimension in this case? Yeah, what is the dimension, but what was the dimension of input x? No, that's just one thing. Nah. What was the complete dimension? There was a batch size, there was a sequence size. It will be 1, 4. I hope everyone remembers how this thing comes from input itself. This was my batch size where I just have a one sequence. I have 4 tokens in that sequence, and this was the D model, or the size of a token. If anyone has a like a generic query where this 8 went, this just went into multiplication with this stuff and then created 5 and 2. It's 1 cross 5 cross. The same thing I have implemented in code itself. So I think इसके आगे का code I have that code. So I think intentionally we have left this code so that you guys can implement the further section for scale dot product, which was again taught in the previous code itself. I'll be receiving 2 values from the scale dot product, values and attention. I'll be just using values here. I'll be reshaping these values by just multiplication of number of heads with the dimension of each token I received. Here it's 64, I think, 64. I'll be getting new vector of size 1 cross 4 cross 5 and 2. About this, everything is there in previous code itself. This is the only thing which changes. So from where we started, we ended up at same dimension itself. We started X with dimension of 1 cross 4 cross 5 and 2, and we ended it here with the same dimension, the final summation dimension with similar dimension 1 cross 4 cross 5 and 2. If I just, I have formulated this complete stuff into one class. Again, in class also, I have just defined one function outside the class, the scale dot product function. I have all my variables which I require. I'll just run this class, and my final output will look something like this. This is the original input. This is the bulk query key value matrix which I have created. This is how I splitted each particular vector for each head. When I split this each head vector into individual query key matrix, I'll getting this dimension. The new value and the attention will be having this dimension. And the summation of all the z will be of this dimension. and this is the final output which we receive. While getting final output, I must have told you that there is this thing. There's this linear layer kind of thing, WO. I have also implemented this linear layer, which is again of dimension D model cross D model. D model here in our example is 5 and 2. This is the complete implementation of multi-head attention. There's nothing new in multiple head attention other than WO. Other things are just carried from the previous scale dot product, the single head attention itself. Here, just we are splitting the query key and value for each head. And then just to make all the weights get shared and all the tensors which we receive get communicate with each other, I just created a linear layer and I pass my new V or the final Z itself from this WO and I get my output. Any questions for this output? Or even any question how this multiple head attention works theoretically or mathematically? All good? क्योंकि इसके आगे का कोड मैंने लिखा नहीं है, वो आपको साथ साथ लिखना है. जस्ट वन मोर कोड इज देयर विद मी. बाकी के मैंने लिखे हैं बट आपको लिखने पड़ेंगे अगर पूरी इनकोडर डिकोडर क्लास चलानी है तो. आई हैव वन मोर कोड which is available on GitHub, that is positional encoding. Do you know theoretically how this positional encoding itself work or not? कि requirement क्या है इसका? Because I can't just stick to one positional encoding की sin cosine वाला ही हमेशा हर transformer based model में transformer based LLM में use आ रहा है. This is just a one representation which initially was given into attention is all you need paper, which is on basis of sine and cosine. Nowadays, this can be absolute also or rotatory also. But do you know what is the use of positional encoding itself? If in one line I finish, this is just to showcase how a particular token in a sequence is context aware of the other tokens which are present in a sequence, so that its representation can be changed over the sentence itself. It doesn't stay to one representation. Like if I have a thing like if I have a sentence like this, Ankit and Sumit were going to grandparent home. This time, even though this word is important, but most of the attention will be toward this thing, grandparent. So there is some kind of communication between this word and this word also to show the attention how these things works. But if I have a word like this time, most of the attention will be given to this word. Even though name is same, but the context would change over the time. Even if I shift this word somewhere in between, the attention will be more toward that word itself. Positional encoding just make everyone just aware where that particular, the most attention valuable word is available. This is just a way to let the transformer know what is the position of that word. That's it. That so initially we receive our embedding of like if I say Ankit and Suk. I have a car. I'll receive 1, 2, 3, 4. These are just an embedding. That doesn't make any sense. They should know where they are present in a sentence, whether a car is present on the last of a sentence, or if I have a car built by Ford, whether it is presenting in middle of a sentence. So this positional encoding holds a value here to represent where that encoding of that particular token is present in a sequence which we have received. I'll not show how this again works in deep. I'll just show how positional encoding in sine and cosine works. What does those represent? And when we show this image, like if I have this circle, how this circle is produced. Addition is just a normal addition of encoding and the positional encoding. But I'll just show how these positional encodings are created. Again, these are also again just randomly generated numbers. These don't hold any value. These are just for a demo purpose. Let's say I have a sequence. I'm a robot. There is an index for each token in a sequence. What we'll call this thing? Forget the whatever value is inside it. What we will call this thing, this continuous array. What is this? I hope everyone is getting my question, what I'm asking. Just forget the numbers or whatever is written. What I'll call this array itself. In terms of token, what is it? Is this for a token? What? No, not binary. I'm not asking at that ground level. This is just a representation of any token I have with the dimension 4. I hope you understand this. So in this example, I'm representing any token which I have in a sequence with a dimension of 4. So in earlier example, if I show where I was having dimension of a model as 5 and 2. Now in this example, I have of a size 4. This is just to show how sine and cosine positional encoding works. For each even, I'll just treat it as even that 0, 2, and 4, and it will go like this. For each even representation, I'll be having encoding from sine, and for each odd representation, odd index of that representation, I'll be having encoding from cos. And this will continue for all the tokens I have respectively. This diagram is just to show that how sine, cosine keep on moving in each embedding. This is the formula we have, which was given by the paper. I have just changed the formula bit. Instead of 2i, I have just kept it as a single I, which will not make a big difference here. Instead of 2i, I have I and I minus 1. This is a same formula. I have even provided the explanation how this formula works. You can read it at your own pace. I mean, not right now, after this. I'll start with a sequence of length 10, and where earlier in our case where D model was 512, now in this case, I have a D model of size 6. I'll start with showcasing whatever are the even index and what are odd index, so that I can apply the sign for even index and cos for odd index. I'll have a even index 0 to 4 and odd index 1, 3, 5. Because I have a dimension D model 6 itself. So these are just a 6 indexes. For each even index, I'll calculate a denominator using the same formula I have given here, this formula. Denominator is this thing, 10,000 power I divided by D model. 10,000 power even I, basically the ith even index, divided by D model. D model is, what is the value of D model? 6. For odd also it will goes like this. If you look closely, both the values are same actually. For both the denominators, values are same. This is because even though indexes are different, 0, 1, 2, 3, when I put it here, it will be 1 minus 1, 0 again, 3 minus 1, 2 will be there. Same thing will happen. So what I got from making this change in formula is I just change my denominator, which will be common in both the cases. I'll be having now common denominator instead of even denominator and odd denominator. I'll just call it as a denominator. I'll be finding out the number of tokens I have in a sequence. Right now I have a 0 to 9, which is 10 tokens in a sequence. I'll apply the formula itself, which is sign divided by position divided by denominator, sign of a position divided by denominator, which is very straightforward here. For even position, for odd position. For even position, I'll receive this value. The first array will be of all 0, but for odd position, I'll be having first array of all ones. So here in this case, this is of index 0, index 2, index 4. And for odd position, this will be for index 1, index 3, and index 5. Now, since I have calculated separate these positional encodings, somehow I have to merge it back so that it can be even, odd, even, odd, even, odd, and the number of index can be continuous 0, 1, 2, 3, 4, 5. There's a simple method for that. One is stacking, and then I'll just flat it. How stackings work is just by example I'm demonstrating. For each 0, I'll be having its representation 1. Let's forget the 0. Let's look from second array. 0.84, I have 0.54, 0.0, and then 0.00. Please remember this. 0.8, 0.0, 0.00. I have a respective cost value also for this thing. 0.54, 0.9, and 1.0. If you want to take a look, these are the same things, secondary of both. And then I'll just flatten it up into singular array. All these 3 array will be merged into singular array. It will be 0, 1, 0, 1, 0, 1, which will look something like this, 0, 1, 0, 1, 0, 1. I got my final positional encoding, which we were looking into this diagram. I have sine, cosine 0, 1, 0, 1, 0, 1. This positional encoding, I can just add up with my original encodings, which I receive from tokenizer for each token. And I can fed this final embedding to my transformer, which I think will be visible here. This is what I received from my tokenizer. This is which just I created, and I'll just push it to my encoder or decoder model, whatever what I have, and then just split it into 3 different vectors. I have just created a simple class for this, which will do all work for this complete code. I hope everyone understand how this positional encoding is calculated. I mean, how sine cosine comes alternatively, how we got that thing for each odd or even index respectively. I mean, you are asking why sine cosines come. The one reason I found is like what they says is at the time when sine is zero, cos is not zero at that time. One of them is having some value holding at that time. So, but I don't, I'm not sure whether that's a right reason. But that was the only original encoding they have given in this. But I don't think so. Nowadays, models are using this encoding. Nowadays, they are either using rotary encoding or something like that. This was just an initial representation they have shown. Even I think they have given diagram in this block itself. This was originally, I think, given in paper also. The reason why they have used this sine cosine. I'll just push one more code here and then we'll start using our own editors. Just take a break. I just have pushed one more code there, layer norm in our repository. You can all clone that too. This thing. I have a question for all. Does anyone know why we call it add n norm? We can just directly call it norm or layer norm itself. Why we call it add n norm? Yeah, we are kind of adding residual connection with a no, one though you got correct. We are adding this residual connection with the new V or the Z which we have received, and we just normalize that complete thing. So it's a first add and then norm. So this is the reason behind this name. So we have received this thing. This Z we have received. This final X or the residual connection itself. This is the connection, but the vector which we are receiving is the X itself, which is formed after how we received X. We received X after the addition of positional encoding and the embedding of those tokens itself. I'll just add both X and the new value and then normalize it. I just pushed the code for layer norm. There are two things. One is batch normalization and another is layer normalization. Anyone knows the difference? Feature wise in the sense. You can even tell in more easier language, that will be fine. We have let's talk in terms of like I have 4 words, 4 tokens. I am a robot, and for each token I have a representation of size 3. Now tell me, how can we do a batch normalization? Yeah, you are correct, you can tell. Will normalize the complete token itself or ith index of all the tokens? Yeah, that's a kind of batch normalization. We keep on normalizing complete batch itself for each ith index we receive. And in terms of layer normalization, what we do? We do token wise, complete token embedding. We normalize that thing. I'll just show how that thing looks with the graphics. This is what a batch normalization looks. I have a one batch with 3 samples. Samples in the sense, samples means 3 tokens. If I say, I have first token, I have second token, I have third token. Each token of a dimension 4, x1, x2, x3, x4. I'll normalize over the index of each token here. I'll calculate mean, I'll calculate standard deviation. Again, in terms of layer normalization, I'll calculate this thing downwise. It will be for complete token itself now. Instead of calculating for one index respectively in each token, I'll calculate for complete token, and I'll receive normalization for each token now. The reason which I got like why they are using layer norm instead of batch norm is it is quite stable and independent of a batch size, whatever we are using. That's the only reason I received. But this is the layer norm they have used in original transformer. So we'll implement that thing. I have already told you like why it is known as add and norm. So we'll add this new V with X dash. X dash is residual or the original embeddings which we are receiving for X. This is the formula for layer norm. I'll align this formula with the image which we have just seen. Just remember this thing. For each X, I have a mean and a standard deviation. So this is a mean and standard deviation for each X. I'll use this thing in formula itself. For each X, I have a mean and standard deviation. These are two learnable parameters, gamma and beta, which are trained over the time with the backpropagation. These are not hyperparameter, these are the parameters. I'll start with a very simple example now. I'll have a batch for 2 words with a sequence with a D model, 3 here. I'll receive this thing from my output. Basically, what my input is of dimension 2 cross 1 cross 3. Initially, I received batch number of words, basically sequence length, and the embedding size. I changed this batch, which was 1, and just juggled the position here. And now I have sequence length, which is 2, batch, which is 1. Each batch has 2 sequence, and the embedding, which is 3. I have hard coded this thing instead of declaring 2 cross 5 and 2 cross thing, because we just have to look on this small example right now. I have a gamma and beta. Uh, Gamma right now initially should be 1, because this is just for a demo. I can't keep gamma 0.0 something or 0 itself, because it will just change my initial values. So I have just kept it 1. And also, so that my input is not hindered, I kept beta 0. So it doesn't change my input right now. Over the time, these things can change, like beta can improve and gamma can decrease or vice versa. So this is how gamma and beta will look. For each sample, gamma and beta will be same here. So gamma will be for all index, it will be 1. And for all index, beta will be 0. These are just a dimension of gamma and beta. If I calculate a mean for each sample I have received, sample in the sense this sample, 2, 1, 3. If I just directly manually calculate mean, it will be 2 plus 1, 3 plus 3, 6 divided by 3, 2. This is the mean I received, 2. And the same goes here, like 0.5, 0.6, and 0.7 divided by 3 will be 0.233. This is the second mean of second sample. You can see this is layer wise, because for each sample, we are calculating their own mean. And similarly, for each sample, we'll be calculating their own standard deviation too, which will be calculated using variance again. This is the final Y which I receive. Y here is this thing, just this thing. For each index, I'll just subtract it with the mean and divide by standard deviation I have. I'll be getting my new Y, and then I'll be using my parameters gamma and beta, which right now in a case is 1 and 0. So it will not make any change. It will be giving me as it is values. This is the complete class I have. Now, instead of hard coding, I have generated a random numbers just to show how layer norms work here in this dummy example. Instead of keeping the range from 0 to 1, I have kept it -5 to 5. I'll just showcase. This is my class. There's one more thing. There's one term epsilon here. What I'm doing with this epsilon is I'm adding it into standard deviation. If we look where the standard deviation is used is here. I have introduced a epsilon, like this is sigma plus some epsilon value, which I think will be very close to 0, but not 0. Can anyone tell why we need to add epsilon? You can be a bit loud. हाँ, there will be nan values there at that case. वो फट ही जाएगा, हाँ सही है. So just to save our weights from getting exploded, we use some very little value of denominator that even in a case our this variance and that standard deviation goes 0, we still have some value which is very negligible. I had just added this epsilon. There's nothing change other than this. We just calculate mean, we calculate standard deviation. For each x, I calculate a new y, and I just output it with the pinch of gamma and beta. I'll just run this class. I have a batch size 3, sequence length 5, and D model is 8 here. So in each batch, I have 3 sequence of length 5 with the range -5 to 5. This is how my each batch is going to look. In each batch, for each sequence, I'll be calculating their own mean and standard deviation, and then calculating their own y. I'll just show one thing. Now for each this thing, I have their own mean. For sequence length of 5, and for 3 sequence, I have 15 means now and 15 standard deviations. When I do that formula wala stuff, x minus mean divided by standard deviation plus some epsilon, I'll get new y. And then I do that gamma and beta. Here in our case is 0 and 1. I'll get final output. You can see that now these are very close to each other. Instead of moving away -5 to 5 range, these are very close to each other. Like in this dimension itself, you can see. Now this -1, 2, or 3 has become 2. So the whole funda of this layer normalization is to normalize these weights to close to mean with a bit of standard deviation from the mean itself. So that in future, after moving from one layer to the nth layer, let's in case even the small models now have 12 layers, it doesn't become very high or move completely away from the x itself. So we keep it close to x by using this layer normalization. Here I have explained everything, why layer norms are used and how this formula is calculated. This was the layer norm add and layer norm, which is going to be same in each, whether we are using encoder or decoder. The method will be same. Now we have covered how many parts in this diagram? We have covered this positional encoding. This I'll receive from my tokenizer for each input. I have covered multi-head attention. I have completed add and norm. The only thing is left is feed forward, which is nothing but just a neural network which expands and contract over the time. That I'll also show. I have to create an encoder class now. The code is not there on GitHub. You have to start coding with me. Even though I have code, you have to start working with me so that I can at any point ask, what does this output represent? You can show. These are the residual connection, just for a clear idea. From that code, can you start working with a scale dot product we have? I think that code is available for everyone on GitHub. You don't have to even write anything so much. You just have to copy paste everything from that code. Please do this. This is, I have already explained in 2 sessions. Yeah, it's a first file and also present in the second file. I'll just show all the classes which you can implement, and you can, whether you want to take break, you can take a break. And if you want to just go with the code, you can go. We have to do this scale dot product function. We have to do this multi-head attention. We have to do this layer normalization. Everything is written in those code. I have written in class format itself. This is the only thing which is left, which is like just a 4-line code, and then there is just a forward pass. This is position wise feed forward that I'll tell after break. And then we just create a encoder layer and call it. So till then you can at least implement this thing, scale dot product, multi-head attention, layer norm. I haven't used positional encoding here because I'm not generating X embedding itself. I'm just directly creating a random values right now. This is the only thing which is left for our implementation. Rest, all of it is being implemented in the previous slides. I'll directly jump to this position wise feed forward. What is does is, let's see if it is present in this. Okay, let's start with our code itself. At this point, we have our, what we have right now at the cursor. We ended up with add norm, which was x dash and z. I got something like this, right? After doing this. I got a final y, which will be our output. The dimension was again same here. This dimension is similar. I'll get a similar dimension here. Let's say if I keep it as 1 cross 5, 1, 2. In feed forward layer, what will happen is I'll just expand this dimension 5, 1, 2, 2. In original paper, they said that we'll expand it 4 times. So it will be 2048. And then we'll again contract it back 2048 to 512. This is just a simple feed forward layer, nothing else. They just want to expand the vector so that weight sharing inside vector can be more, and there can be easy communication after we have created this z and that x. Now I get a new layer where they can share their weights. That's the only reason they are using, it's a kind of feed forward layer. How they implemented is they added 2 new things here. One is just a ReLU activation function. I hope everyone knows what ReLU does. If I just showcase in simple form, whatever x is in negative and whatever x is in positive, it just keep it 0 whenever it is negative, and whenever it is positive, it will just shoot up. This is just a ReLU activation function, which is easily, I think, commonly used in most of the neural network, but nowadays people are moving over it. Like in GPT-2, they are using this GALU is being used with the 10H approximation. Other things are also there. CELU is there. Leaky ReLU is also there. This was the original one, which was given in Transformer, the ReLU. There is one more thing here is dropout. Does anyone knows what dropout is? Or how does dropout work? Yeah. Uh, why we do that? Kind of, but there can be much better answer. No, it's not necessarily for improving the training time. वरना वो छोटा न्यूरल नेटवर्क ही बना लेते अगर ट्रेनिंग टाइम ही बढ़ाना होता तो. हम्म. What was your answer? Yeah, it was kind of that thing, the reason behind. So I'll just create a dummy neural network. What happens is let's say each of them are communicating with each other in a traditional feed forward way. If I set my dropout 0.1, this means I'll switch off my 10% of a neurons here. Let's say I have switch off this one. And then in this layer, 10% will be I have switch off this one, this one. So if I create a path, let's say they are transferring their knowledge with each other. Initially, the path will look something like this. But I don't want to get this path over the time and they overfit on this path always. What I'll do is I'll just switch off this one. And now it has to generalize over other things also. There's another explanation also. They are kind of mimicking multiple neural network in the same neural network itself. So one time we have a neural network which don't have these neurons. These are absent. So for my current transfer of this data, I have this small neural network. Other time I'll just switch off these neurons, the new neural network will occur. So they are just using a same neural network and kind of mimicking, they have multiple neural networks so that it can generalize over the time in much better way. Dropout just means dropping out those percentage of neurons. These are the two values which we have other than just a basic feed forward layer. In a forward pass, it's again simple. I'll just take 512, which will be transferred into 2048. I just shown there. I'll use my ReLU. I use my dropout. And again, I'll transfer it back from 2048 to 512. That's a basic feed forward layer. How the complete pass happens is, I'll just show here, it's much better. Let's start by creating our encoder itself. Let's start by just, I want everyone to remember this image, so I'll just draw it here. This is the architecture of neuron, this encoder itself, which have this as a residual connection. And this is our multi-head attention, layer norm, feed forward network, and then layer norm, and the final output is given away. Let's declare our encoder class. I'll directly start from a forward pass and I'll use whatever I've used. I'll initialize my initial X as a residual X or X dash, whatever is suits you. I'll initialize my attention, which is multi-head attention. I will initialize a dropout. This I haven't told, but they use this dropout after each Z value which we have created, the final Z we have created after multi-head. So this dropout comes inside this part. Here this dropout will happen in embedding of each token. So it will just switch off some of the indexes and will move further. I'll use our first norm one, add a norm. I have X, which I get from self-attention and after getting dropout. I have my residual X. I have my second part now, positional encoding. Positional wise feed forward, which is this FFN. Before that, I will initialize this residual X. This is my FFN. I have second dropout before it enters layer norm. I have my norm 2, which have this X, which I receive after dropout 2, and this residual connection 2. And then in the end, I'll get my final X. In the file which you have received on GitHub, I have explained why we require dropout, why we require residual connection, what is use of it. In simple ways, I have already explained you. Residual connection is just to improve the already existing and just to introduce already existing values, and it also used in backward pass so that gradient vanishing problem doesn't occur. Since I'm not explaining backward pass in transformers, so I have just explained it here. I'll just call my encoder for the number of layers I have defined. These are my parameters. Dimension of a model is 512. Each token will be having a vector length 512. Number of heads I have is 8. Dropout probability is 0.1. I mean, 10% neurons will be drop out at a time in single forward pass. Other time it will be something else, some other 10% neurons. Batch size is 30. At a time, a batch can have a 30 sequence. Max length of each sequence is 200. Dimension of a FFN is again 4 times of a initial D model, which is 2048. And number of layers are 6. 6 times this encoder will replicate itself. Here I'll just start running this. I'll just start from top. Let's start with whatever the dimension outputs we have received. I hope it is visible to everyone. We'll start with our initial vector X, which is of size batch size 30. Each sequence with a max length 200, and each token in that sequence is represented by 512 vector length. I'll start with QKV, where like in scaled product or in multiple head, where we initialize this QKV. I mean, why we even required QKV, this vector? Can anyone tell? I just explained everything. I'm expecting at least one of you tell. Why we required this vector? Yeah. Yeah, so I told you earlier itself ki instead of creating WQKV separately, I'm just chunking it as a one vector so that each head has initially a 1536 size embedding, which will be splitted for each head. And after each head will receive this embedding as their initial starting point. After that, I'll do scaling. Once I calculate matrix multiplication, I'll do scaling. After scaling, my value will be of this size and my attention will be of this size. My final value after merging all the heads will be 64 cross 8, 512. And this will be my first output from my first multi-head in a single encoder layer. I'll do my first dropout here. I'll start with layer norm. In layer norm, for each sequence, each token, I'll be having their individual mean and their individual standard deviation. I'll calculate a y with the help of mean and standard deviation. I'll be having two parameter gamma and beta, which in this case are 0 and 1, 1 and 0. After that, I'll get my final output, which is 30 200, 512. I'll pass my this layer norm output to position wise feed forward or FFN, which will expand it from 512 to 2048. I'll be having ReLU activation. I'll be having dropout. And after that, it will contract back to 512 from 2048. I'll do my second dropout. I'll repeat the layer norm again. I'll get my output from my first encoder layer, which will be fed to second encoder. If we look, this was my initial input, 30, 200, 512. This is my output, 30, 200, 512. Same thing will go to second layer, where again it will be expanded to 3 different vectors. In the final, after completion of this, all the encoder layers, I'll receive a output which was of a same size, which we started with initially. This is how a vector which enters, whether in individually or in a batch, shapes over the time in encoder as it passes through multi-head attention, layer norm, position-wise feed forward, and then again layer norm. And it gives its output after completion of all the layers. I hope every one of you understood how encoder changes the data, whichever we fed it into it. Anyone is still unclear about how vectors are getting transferred or transformed in encoder? I'm expecting everyone is done with this thing. Let's do live work now. Yesterday, I think Sir taught a BERT, right? BERT, what was the parameter of those BERT? If anyone of you remember. How much? No, I'm asking the total number of parameters in that model. 110. Now let's calculate how that we received that 110 on board after looking into this code. I'll initialize few values. I want everyone to use their paper and pen because this is just a look back to whatever we have just done now. I'll start writing the parameters here. You can just note it down so that we can start calculating all the parameters together. I'm expecting everyone has noted down these parameters. We'll start working on this. I want if everyone is aware what these parameters are at least. ऐसा कोई, if anyone doesn't know what this parameter is, can ask me. Which one? Just now I explained in original transformer, when they are creating this FFN, they says this is 4 times the dimension of a model. That's why I have written 4 times dimension of model. Okay, just read them. First one is number of layers, which are 12. Second is the embedding dimension, that is D model, is 768. Third is number of heads we have, 12. Fourth is vocab size, that is 30,522. Fifth is hidden embeddings, for that FFN is 4 times 768. Sixth is max sequence length, that is 512. Let's start with embedding metrics itself, because those are also learnable parameters when we define our vocab. What will be my vocabulary size? What will be the dimension of my vocabulary? This is my vocabulary into 768. Then we have positional encoding also. Even though the thing I have taught you, sine and cosine, are not learnable parameters, but in BERT, they are using learnable matrices for their positional encoding. What can anyone guess what will be the dimension of a positional encoding? How much? What is n? How? Yeah, what is the number of words? No, I have just written maximum sequence length, 512 cross 768. Since this is BERT and which is encoder model, they use something known as type of tokens. If you remember from the BERT architecture, there is something type of tokens. They, in very simple example, if I explain, when you pass question and answer to a BERT, or you pass two sentence, sentence A, sentence B, you want that BERT should know that these are two different things you are passing. So just to showcase it in embedding form, it will assign 0 to sentence 1 and 1 to sentence 2. And it will keep on doing 0, 0, 0 for whatever the number of tokens we have. And here in our case, what will be the maximum number of this 0, 0, 0 for each word will be? No, for each word I'm asking. 768. And it will be repeated how many times? Since I'm passing two sentence, it will be 2 times. Just to showcase what is the type of sentence. Third thing, the last thing is, in barebone transformer, they doesn't use any kind of layer norm, but in BERT and other LLMs, whichever you'll use, they use a final layer norm after using this summation of encoding, the original encoding and positional encoding. They'll use one layer norm. For layer norm, I'll tell the dimension just once. It will be 768. Okay. These will be the weights, and same number will be the bias. Please sum this up. It's a 30,522 into 768 for original vocab. For position, it is 512 cross 768. For token type, I have 768 into 2. And for the layer norm, I have 768 weights plus 768 bias. One of you, please tell me the final answer. What is the answer? You can just recite the digits itself. 2, 3, 2, 3, 8, 3, 7, 1, 8, 4. So this is roughly 24 million. Just if round up to 2 digits, it is 24 million. We'll start working after the I get a embedding that X thing. I'll just refer to a diagram. I have this thing X right now. I need to convert it into query key and value. What I need? I need something to split it up. I just also shown it here also. What is that thing? There's WQ, WK, WV, right? What was the dimension of WQ, WK, WV? No, it will be not 512. Yeah, it will be 768. 768 cross 768. Let's keep it simple. It will be 768 cross 768. And there will be weight. This is weight, and there will be bias of 768. And such we have how many? How many metrics we have such like this? How many? Three. I have one extra W also. I told you. What is that W? I told you after I get sum up of all the Z's, Zn, Zi, Z0. If I get a final Z, I'll pass it through one linear layer. What will be dimension of that linear layer so that original size still get maintained? 768 into it will be 768 itself because I want output of 768 dimension. So it will be 768 cross 768 plus bias 768. Which one? This one. You remember there is one layer after I do my all the Z summation and I pass it through this linear layer so that all the heads output, whichever is there, which I just submitted, can communicate and share weights with each other. So I have one WO matrix kind of thing. If you want to look, it will look something like this. This thing, WO. In this diagram, once I cross this multi-head attention, what I'm going to target? What? Add and norm. Dimension of add and norm will be, I just told it here. 768 cross 7 plus 768. What are the total parameters I have received? Initial is 3 into 768 into 768 plus 768 for all the query key and value matrices I have. Then I have for WO 768 cross 768. This one is WO. This is layer norm. What is the value? What is the value? आंसर आया किसी का? Not in terms of like just recite a number. Two, 3, 6, 3, 904. How much? That's it. Is it this much? That's it. No, I'm asking for this calculation itself. Are you sure? We missed one thing, right? I mean, two things. We forgot about feed forward layer itself again. So it will be and that's correct till this point, but I want a complete summation so that we can 768 cross. There will be 4-time expansion. It will be 3072, and then there will be summation of the biases, and then again there will be contraction 3076 768 plus 3072. And then I have one more layer norm after feed forward layer. It will be again this thing 768 cross 768. Can you just quickly sum this up also in this thing? This is 768 cross 3072, and again it will be twice, and then there will be summation of 768 and 3072 as a two different weight biases. And then this is just a layer norm. Can you tell me final summation after this value? What is this value? How much? 70, 8, 6, 3, 3, 6. This is just for single layer. How many layers we have? Just multiply this with 12. How much? 8, 5, 0, 3, 6, 0, 3, 2. It's fine till last digit. It will be roughly 85 million. I'll show something. The way there's this linear layer after decoder, in BERT, there's one linear layer which is present after encoder itself. So it will be also 768 plus 768, not plus, it will be linear layer, and then there will be some biases, 768. If I just sum up this thing, 85 plus 24, this will be somewhere around 500,000. If you do calculation, it will be 9, 10, and then there will be 500,000 from there. And also we have just rounded up some here and there. I have parameter which is 109.5 million, which I can just roughly say it's 1.110 million. This is the original parameter count which BERT 110 stated. These all the parameters which I have just derived are from the code which I have just done for encoder itself. अगर अभी भी किसी को समझ नहीं आ रहा कि कोई भी पैरामीटर कैसे डिराइव हुआ है, they can ask me, because everything was there in code itself. Yeah. Hmm. What?
That part, na.
Mhm.
You do multiplication in WQB matrix
Yeah.
many times. We add some bias,
Hmm.
768. Why? Because we have the matrix parameter, no?
It's a kind of linear layer itself. And each linear layer, there is bias na? After every linear layer, 768 plus, there will be a neural network kind of stuff, 768, 768, 768, 768. I'm calling this as a matrix. In neural network, in each neuron, you have some bias, no? 768, 760. For each layer, you have some bias. I hope everyone is clear with how we derived this BERT from our encoder. I'll just give a glimpse of how decoder looks and what is different in decoder, because I think we don't have much of time left. What is the extra thing here in decoder? Can anyone just point it out quickly? There's this masked multi-head. That mask which we kept optional will not be optional here, will be mandatory here because this is decoder part. I have multi-head, which can be known as cross attention also. Why cross? Because we are using cross from decoder encoder part and decoder part. Here, from here, I'll receive key and value, and this will be query part. And then instead of 2-layer norm, I have 3-layer norms here, and this will keep on repeating until the number of layers I have declared. Other than that, everything is pretty same. I'll just hover over. I have same scaled product. Now I have mask here. I have a multi-head attention, which is mask multi-head attention. I have a layer norm. I have this cross attention. I'll show how this thing works. From decoder, I'll get query this key and value of. From encoder, I'll get key and value. Let's say I'm translating something from English to Hindi. I put something in English in encoder part. I want something in Hindi part. So the embedding of English token I'll receive from encoder will be in form of key and value. And what I am going to generate in Hindi will be having embedding from decoder itself in form of query value, query vector. Again, these are just two origin. Inside calculation is going to be same. In the end, I'll be getting this key value, which will be reshaped and then chunked down to 64 size vector itself. I have printed the shape of all vector here. I'll just run it. Same forward layer FFN is there. Let's come directly to decoder class itself. What I have here is, I'll start with residual connection. I'll use self attention, which is masked this time. Decoder mask is there. I'll use first dropout, and I'll use layer norm first one. After that, I'll get Y, which I'll save as a second residual connection. I'll use encoder decoder attention, which is cross attention wala part. I'll use second dropout, second layer norm. I'll save as a residual connection. I'll use my FFN, dropout, third dropout, and I'll get a final Y. I'll just call it as a number of layers I have given. If I just showcase the parameters or the size of the dimension of the vectors, it will be pretty same, except I have one more chunk now, which is cross attention wala part. So I have multi-head attention one, where query key and value are there, scaling happens, new value is created. I have first dropout, I have same layer norm. I have second cross attention, where I get key and value from encoder and queries from my own decoder. Again, same scale dot product will happen and I'll get new value. Again, dropout 2 will happen. Same layer norm 2 will happen. I'll pass it to position wise feed forward. Another dropout will happen. Another layer norm will happen. I'll get a final output, which is again of same dimension 30, 200, 512, which was the original input. This code is available on the GitHub, which you can easily clone and run. I'll not run it because we are done for day. I'll push this one also. There's a complete implementation of transformer. Because we have just studied encoder and decoder, this is the same thing. It will be having, if I just show you the class. One time I'll call encoder, one time I'll call decoder, and one time I'll call the final linear layer, which I just shown this linear layer. That's it. I hope everyone understood how transformers work now. I have provided all the references on my GitHub. I'll just whatever sources I used. I have a complete code here. Anyone can clone and use it. I mean, this code will directly not work in your environment because this was for demo purpose. But whenever even you are going to implement original LLM based on encoder or decoder, both encoder, decoder, these are the same layers, same functions you have to implement in similar fashion. Any question? Thank you.